I'm Venkat Guruswamy. I'm a senior scientist here at the Simons Institute, and it's my great pleasure to invite you all to the boot camp of the MetaComplexity program this spring. And as you know, the Simons Institute is a leading center worldwide for collaborative research in theoretical computer science. It was established in 2012, more than 10 years ago, with a generous grant from the Simons Foundation, and it continues to operate with generous support from the Simons Foundation and various partners. And each semester, the Institute brings together the world's leading researchers in some topics, as well as the next generation of outstanding young researchers. So typically, we run 2 programs each semester, each of which brings about 70 visitors, long-term visitors, junior and senior, plus visitors for each workshop. And this is actually the 10th year of programs at the Simons Institute. We started in 2013 with the actual programming. And I think we and the whole community can feel proud of the achievements of the programs, which have really pushed the frontiers of the field in so many directions, solving long-standing old open problems, making progress on them, as well as opening up new directions of inquiry and connections to other sciences, engineering, humanities, and so on. And this semester, we have a program on MetaComplexity, as well as an extended reunion on satisfiability, theory, practice, and beyond. And I believe that program, the reunion also has a lot of connections with this program, so that should be exciting in the second half of the semester. And this week, we kick off the activities for the MetaComplexity program with a boot camp. And for those who may not have attended one of these, a boot camp is intended to acquaint program participants with the key themes of the program. And it'll consist, in this case, of 4 days of tutorial talks by leading experts on the topics of the program. And our sincere thanks to the organizers of the program and also this boot camp, who are Tony Pitasi. If you're here, wave your hands, but I'm sure everyone knows you all. Rahul Santhanam, Valentin Cabinets, and Rafael Paz. I see at least 3 of you here. So thanks. Let's give them a round of applause. And before I hand it over to Rahul to introduce the workshop and give the first talk as well, a few logistics for the coming week. First of all talks are live streamed as well as recorded for posting on the Simons website, and where they enjoy a life and impact long after the bootcamp winds down. And especially for the bootcamp, these talks have really served as a valuable resource for students and researchers worldwide to learn the state of the art about some very important topic. So, I think they're a great resource, even more so for the bootcamp. And some other sort of logistics on the week itself. Food is provided before the first talk and during the breaks just outside. For lunch, you're on your own, but there are many options within walking distance. And we have also arranged the weather to turn back to its normal good for this week. So there should be no problem walking to get lunch. And we do request sincerely that you leave all food and drinks outside before entering the auditorium. So that keeps the auditorium nice and clean as it is now. And if you do need to store something during the day, so there are lockers on the other side where you can lock your valuables. And our videographer, Umaid Far, is around to help with all speakers and setup. So if you have any issues setting up, it should not be a problem. And I believe this is not hybrid, right? Is there a Zoom thing going on? Oh, okay, so there should be a Zoom link, but I don't know whether the session chair is monitoring, but you can. And finally, before I hand it over, a special round of thanks to our events team, Kelani Penland. She's there, waving, find her if you need anything. And she's also helped by Ashley Hassan and Elizabeth Yuen, who should also be around this week, for managing all the logistics to arrange this. And it always goes very smoothly, and sincere thanks to them. And with that said, without further ado, I'll hand it over to Rahul to introduce the program and the plan.
Thanks, Venkat. Yeah, it's great to see so many of you here. I'm Rahul Santhanam. I'm one of the organizers of this program and of this workshop. So thanks, first of all, to the Simons Institute for all their support for making this possible and for the organizational help as well. So just to give you a sort of plan for this week. So the bootcamp is really meant to get you all up to speed, able to talk to each other. You might be from different backgrounds, computational complexity, proof complexity, crypto, and to just sort of get you up to speed on the basic concepts of the area of MetaComplexity. So there's going to be 4 days of talks, and the first 2 days are going to be mostly about complexity theory and learning theory. The third day is going to be about crypto, and the fourth day is going to be about proof complexity. So just in terms of the schedule, there's sort of like potentially a couple of changes. So one of our speakers for tomorrow, Shuichi Hirahara, is unwell. So we're not quite sure he's going to be able to make it here in person. So he's either going to be giving his talk online live, or he's going to be recording it, and it'll be available for you to watch later. And we'll let you know about that later today, depending on how he's feeling. And on the third day, the original order had Tal Malkin and then Rafael pass, but now it's switched, and Rafael is speaking first and Tal is speaking in the afternoon. So it's just sort of minor changes in the program. With that done, let me sort of get right into it. So what I'm going to be doing this first talk is just going to give you a very basic introduction and overview. So just what metacomplexity is about, what the basic notions are, kind of like what the basic vocabulary is, and so forth. Feel free to interrupt me at any point and kind of like ask questions. It's meant to be interactive. And this is really meant to set the stage for the speakers later. So for Valentine later today, and for the speakers in the following days. And so you might see something for the first time here and then see it again on a later occasion, and that's how it should be, because we'd like to re-emphasize things, the more important things, so that they're clearer. So let me get started. So first of all, like, what is metacomplexity? So it might be a relatively new term for many of you, and it's an area that's seen a lot of research recently. But what does it refer to? So essentially, metacomplexity refers to the study of computational problems that are themselves about complexity. And sort of the prime example, the one we'll be starting with in terms of the discussion, is the minimum circuit size problem. But there's also more classical problems, such as the problem of computing Kolmogorov complexity. And there are various others which we'll survey in this talk. And I think of metacomplexity myself in two ways. So one is sort of like a narrower way, where metacomplexity is as a topic. There are all these computational problems about complexity, and you want to understand which complexity classes do these various problems lie in, what complexity low bounds can we show for them, what reductions exist between them, and so on, what kinds of relationships exist between these problems. So that's sort of like a narrow interpretation of metacomplexity. But eventually, I mean, the motivation comes from elsewhere, and we'll be more interested in the broader interpretation, which is metacomplexity as a tool. Really, we are interested in metacomplexity because it's relevant to fundamental questions in many other areas, not just in computational complexity, but also learning theory, cryptography, and proof complexity. And so we're interested in using the ideas, the concepts, the techniques as tools in attacking these fundamental questions. And through this bootcamp, hopefully you'll get a much better idea of how that will be done. But I'll give you sort of a sense of it here in this talk, using several examples. Okay, so in this first 1 hour, I'm going to be focusing mostly on metacomplexity as a topic, introducing you to various complexity measures, the computational problems that are associated with them, what is known about their complexity, and so on. And towards the end, I'll say a little bit about metacomplexity as a tool, but that's going to be reserved mostly for the next talk, where I'll kind of illustrate it through 10 major open problems in these areas, all of which metacomplexity is relevant to, just to give you a sense of which kinds of problems we might be interested in addressing through this program. Okay, so sort of like the key problem that we're interested in is a minimum circuit size problem, MCSP. This problem is sort of like a fundamental problem which has been studied for a while, and especially in the past couple of decades. So the problem here is that you're given the truth table of a Boolean function f, so function from n, little n bits to 1 bit. So the truth table has size 2 to the little n, and a parameter s. And you want to know, does f have Boolean circuits of size at most s? Okay, so that's MCSP. So you're given both the truth table, which is this long string of exponential length and the input length of this function f, and this parameter s, which the sensible values for s are anywhere between 1 and 2 to the n. And you want to know whether f has circuits of size at most s. And then there's sort of a variant of it. So there are many, many variants of these metacomplexity problems, and as the talk goes on, we'll see more and more of them. But for now, we'll just see these two variants: so the minimum circuit size problem and the parameterized variant, where you also have some function s, which is sort of given in advance. Let's assume that s is some polynomial time computable function. that sort of maps the length of this truth table to some number. And the question then is, given this truth table, you don't have this number as a parameter anymore, but you ask whether f has Boolean circuits of size s as a function of the truth table length. Okay. One way to think of MCSP is as an example of a black box problem. So in what sense is it a black box problem? We're given some sort of explicit representation of a Boolean function, that is its truth table, and you want to know something about programs or circuits computing it. You want to know if it has some sort of succinct description using circuits. And well, you might wonder, you're given the complete truth table. So in what sense is it black box? It's black box in the sense that you're kind of given the input-output behavior of the function. You're given for each input, whether it's the input evaluates to a 1 or a 0. So you're given the input-output behavior, and you want to know something about what the computational complexity of this function is. Does it have small circuit complexity or not? So yeah, it's sort of like, very roughly, it's a black box problem. And by interpreting a string as a truth table of a Boolean function, we can think of circuit size as a complexity measure of a string, right? So for any string, so it might not be of length 2 to some power, to some integer power, but let's assume that you sort of like truncate it so that the length is a power of 2. Just consider the first, so if the string is of length between 2 to the n and 2 to the n plus 1, you just take the first 2 to the n bits. And you can think of that as a truth table of a Boolean function, and then you can ask about the circuit size of the Boolean function. So that gives you some sort of complexity measure of a string, telling you how simple or hard that string is. And in a way, what MCSP is doing is answering questions about complexities of input strings. It's a computational problem that's naturally associated with this measure. And what we'll be doing is we'll be defining various other complexity measures, defining computational problems that are associated with them, and asking questions about these computational problems, complexity questions about these computational problems. Okay, any questions so far? Yeah.
So should that be S of log n? Does f have Boolean circuits of size s log n?
Yeah, so you can kind of like think of it either way. For now, I'll say S of n because that's the convention we're operating through the stock, but it makes more sense to say S of log n because say it's exponential size and you want it to be S to be 2 to the epsilon n, for example, yeah. So yeah, according to this terminology, S that's polylog n corresponds to polynomial size. Okay, so just very briefly about why MCSP is interesting from the point of view of complexity. I mean, we'll have more to say about that later, but just for now, a sort of a basic observation, which is that there's the long-standing problem of asking whether exponential time has small Boolean circuits. So we don't know whether exponential time requires super polynomial sized Boolean circuits. And that question is essentially equivalent to explicit constructions of no instances of MCSP. So it's equivalent to efficiently constructing no instances of MCSP with the parameter s of log n of size n given input 1 to the n. So yeah, why is that? So so in one direction, so we want to show that these two things are equivalent, that the circular bounds for exponential time is equivalent to these sort of efficient constructions here. And efficient construction, I mean a construction that runs at time polynomial in capital N. So suppose you had an efficient construction of no instances of MCSP, namely given 1 to the n, you're constructing some truth table of size capital N that is a no instance of MCSP of s of log n. Well, that gives you a way of generating the truth table of a hard Boolean function, because that's what a no instance is for MCSP. Like if you generate a truth table efficiently, you're generating the truth table of a hard Boolean function. And if you can generate truth table of a hard Boolean function in exponential time, then that defines an exponential time language, right? You can kind of like look up the value of the, suppose you're given an input x, you can generate the truth table in exponential time and then look up the value for x in the truth table. So you can solve that function in exponential time. So in one direction, this efficient construction gives you exponential low bounds for exponential time. And in the other direction, if there's a language in exponential time that doesn't have small Boolean circuits, then we can just take this language and generate a truth table in time to the order n, just by sort of running the exponential time machine for it on all 2 to the n inputs. So that takes time 2 to the n times 2 to the order n, which is exponential in all, and it gives you a truth table of length 2 to the little n. And that's generated in time 2 to the order n. And this truth table, so thinking of 2 to little n as capital N, is of size capital N and is generated in time poly of n. And this truth table is going to be a no instance of MCSP of s of log n, right? So it's a fairly straightforward sort of connection between these two problems. And I just point this out because it kind of like gives you some indication of what makes MCSP a tricky problem to analyze. If you think of like most problems that you encounter, generating yes or no instance of them is fairly easy. Like for satisfiability, if you want to generate yes instance or no instance of satisfiability, that's trivial. Just generate a formula which is just x and so on, or you can generate a formula that's not unsatisfiable, like x and not x. So that's easy to do, but it's not that common perhaps to come across computational problems where explicit constructions are difficult. Yeah.
Is there any infinitely often subtlety here that you construct these things only for infinitely many lengths?
Yeah, so if you can construct this for, if the efficient construction works for all input lengths, then you get an almost everywhere low bound. And I think you can prove like an infinitely often version of that as well. Yeah. Okay, so what can we say about the complexity of MCSP? Well, first of all, MCSP is an NP, and that's not too hard to see, though. I mean, if you're not used to working with this problem, it might seem kind of like odd at first. So why is MCSP an NP? Well, you're given the truth table, y, which is of size capital N of a Boolean function f, and you're given a parameter s. How do you solve this problem in NP? You guess some circuit C for f of size s. Note that the only sensible values for s are at most capital N, because if the function has small circuits, if the function has circuits, it has circuits of size at most n. So you can assume that the parameter s is at most n. So we guess a circuit of that size, and you check that y is a truth table for the function computed by C. And you can just do that by kind of running C on every possible input in this truth table. So there's capital N many inputs, and you just run C on every such input and see what value it outputs. And each such run takes time poly of S. And so the total amount of time for running C on all of these inputs is poly of S times N. And we just verify that C of Z is consistent with Y, with the Zth bit in Y. So Z indexes some bit in Y, and you check that that bit is consistent with C of Z, is the same as C of Z. And if you do that for every kind of bit of the truth table, then you know that this is the correct circuit, right? So the point is that this whole check time is polynomial in the size of the truth table. I mean, of course, it involves kind of like running over every input in this truth table, but that's okay because you're given the entire truth table as input. So this is a polynomial time check, and hence this is an NP problem. So yeah, one of the main open questions about MCSP is it in P? And we don't believe that it is. Like the naive algorithm for MCSP is to run over all possible circuits and check if they work, right? So if you want to know if there's a circuit of size at most S, you kind of try every possible circuit of size S and check if that computes Y correctly. That's going to take exponential time. And there's some evidence that MCSP is not in P. If one-way functions exist, we know that MCSP is not in P. And that builds on pseudorandom function generators, which are kind of shown to exist by Goldwasser and Micali based on standard crypto assumptions. And then Rousbrown, Rudich, and Cabnets and Tsai use this to show that connection between one-way functions and MCSP, not in P. And well, the other question then is, if we believe MCSP is not in P, what can we say about the hardness of MCSP? Is MCSP NP complete? There's been kind of like varying sort of beliefs about this for a very long time. I mean, it seemed there were more obstacles showing NP completeness than any evidence that MCSP was NP hard. But slowly over the past few years, there's been sort of a lot of progress on this question. And Rahul Elango will be talking about this tomorrow. And very recently, Shuichi Hirahara showed that a version called partial MCSP, which seems very similar to MCSP. Instead of being given the truth table of a Boolean function, you're given a truth table with some don't know symbol. Some positions you have a don't care symbol. It could be either a 0 or a 1. And you want to know that there's a circuit that's consistent with this, whether on all the zeros and ones, the circuit evaluates correctly, and the don't knows, you don't care what the circuit does. So that's a version of the problem which is very similar looking to the problem. And this version is NP complete. And so are some other kind of quite natural versions. So there's this result, there's several other results, which I'll kind of talk about later. So there does seem evidence now that MCSP is likely NP complete, but we're still not quite there in terms of having a proof. Yeah.
So given this result and what you said earlier about explicit constructions, does this mean we now have efficient ways of generating hard partial truth tables? And is that something that we already knew before this?
Yeah, well, so actually these kind of reductions are randomized. So yeah, so yeah, randomly we can generate.
Yeah, all right. Fair.
Okay, so let me just say something very brief historically. I'm not going to spend much time on this because this is really about like getting up to scratch on these complexity measures and the problems related to them. But it's interesting that, I mean, though MCSP might not be a problem that you've kind of like heard about that much, it's been studied for a very long time, since the 1950s actually, by by theorists in the Soviet Union under different names, long before there's even any work in complexity theory in North America, or even before NP versus P was kind of like stated as an open problem. And there's this great survey by Trachtenbrot, which talks about this early kind of like work on MCSP and related problems. And in fact, Leonard Levin, as reported by Eric Allender, delayed publishing his results on NP completeness. He had all these results on NP completeness, but he really wanted to show that graph isomorphism factoring and MCSP were NP hard. And so he kind of delayed publishing his results, thankfully not for too long. And he did publish it in enough time to get credit for it in 1973. But this is one of the problems that he was stuck on. He wanted to show that MCSP was NP hard. And the recent interest in the problem really follows on kind of work of Cabinet and Sai, who defined the problem and kind of like showed various kind of interesting things about it. And that itself builds on work of Rasparov and Grubich and their paper on natural proofs, which is really about metacomplexity in disguise. And there's a few other sort of important papers in this area which sort of trigger a lot of work, but we'll get to them as we go along. So as I've said before, I mean, MCSP is intuitively a black box problem, right? You're given like the input-output behavior of a function by its truth table. We're given explicit representation, and you want to know if this Boolean function has small circuits. What about white box problems? So MCSP is sort of like a canonical example of a black box problem, and the canonical examples of white box problems are Boolean satisfiability and its variance. So these are sort of like inverse problems. You're given the representation of a Boolean function as a formula circuit, and you're asked information about the function computed by these by the formula circuit. So for example, whether the function has a 1 in its truth table as Boolean satisfiability, the question of how many ones it has is counting sat, and so on and so forth. So like the white box complexity essentially corresponds to saying something about the function given its representation, while with black box problems, you want to know something about the representation given the truth table or given black box access. So it's kind of interesting to compare these two kinds of problems to each other. Of course, we know a lot about satisfiability. We know that satisfiability is NP complete, and this has been used to show many other problems are NP complete. In practice, we use SAT and SAT solvers to solve NP hard problems by reducing them to SAT and then running a SAT solver on them. So the NP completeness of SAT has various practical implications as well. It allows us to solve problems very kind of efficiently in practice. And then, of course, there's lots of theoretical sort of implications of the NP completeness of SAT and work that builds on it. For example, PCPs for SAT are the basis for theory of approximation for NP hard problems. And SAT is sort of like key in many, many areas, logic and verification, sort of parameterized complexity, average case complexity, and so on. And then even from the point of view of low bounds, there's sort of the algorithmic approach to circuit low bounds of Williams, which goes via satisfiability. It's via designing non-trivial algorithms for satisfiability, for circuit satisfiability. So non-trivial algorithms for C-SAT, where C is a class of circuits, imply C low bounds for non-disjunctive exponential time. So, so that's kind of an interesting connection, which goes via SAT and tells us something about low bounds. So on the other hand, we know much less about MCSP still, despite all the recent work on it. And part of the project of MetaComplexity of this semester and all the work that's happened so far is to understand MCSP and its relatives that we'll be looking at soon, defining and looking at soon, as well as we understand SAT, trying to understand the relationship between them better and their complexity better. So SAT has various nice properties. We can ask if MCSP and its relatives have such properties like search decision reductions and so forth. SAT is sort of like extremely kind of relevant to other areas, both in theory and outside, and we can ask whether that's the case for MCSP. And of course, we also want to understand the relationship between MCSP and SAT better, between black box complexity and white box complexity better. So that's sort of like the overarching sort of theme. So there are many variants of satisfiability for any circuit class. We can define C-SAT, which is just satisfiability for the class C of circuits. Similarly, there's variants of MCSP corresponding to other circuit classes as well. So given any circuit class C, we can define the problem C MCSP, where the input is a truth table of a Boolean function f and a parameter s. And the question now is whether f has C circuits of size at most s. Intuitively, you might think that C MCSP should be harder if C is a more powerful class. So for example, if general Boolean circuits, maybe it should be hardest of all because it seems much more difficult to know whether a truth table has small Boolean circuits than say whether it has small DNFs. DNFs are easier to analyze. But this isn't formally the case. We know it's the case for satisfiability, that if C is a more powerful class, then then SAT reduces to CSAT. So if C is a more powerful class than C prime SAT reduces to CSAT. But this is not the case in general for MCSP, and the kind of the complexity can be potentially be non-monotone in C. So as the power of C increases, the problem could either become easier or harder. We don't really know which is the case. So for example, it's been known for a very long while that DNF MCSP is NP complete. So if C is a class of DNFs, then it's in fact NP complete, whether a truth table has small DNFs or not. And this is using a reduction from set cover. However, NP complete is the MCSP, which is about general Boolean circuits, is still a major open question. So if the complexity was monotone in the power of the circuit class, and this should be harder than this, and we should automatically have NP completeness. So it's interesting. In general, we understand C MCSP better the weaker C is, and this is related to the fact that we can kind of like we have better understanding of circuit low bounds for weaker C. So that's related to the understanding of C MCSP as well. So for example, we know that DNF MCSP is NP complete, but we also know that we can approximate the minimum size of a DNF computing a truth table up to like a log capital N factor using approximation algorithm for set cover. And we don't know any such approximation for MCSP. So while DNF MCSP is NP complete, it also has some approximation algorithm with a good approximation ratio. And that's because we understand DNFs fairly well. Any questions about this? So this is, so we've seen MCSP, we've seen MCSP of S where there's a parameter, and now there are all these variants based on the circuit class and changing the circuit class. And now we're going to go into other complexity measures, define other complexity measures and meta-complexity problems based on them. So as we said before, circuit size can be thought of as a complexity measure in strings, and MCSP is a computational problem corresponding to this complexity measure. And similarly, we can consider other complexity measures and the computational problems corresponding to them. So for example, we can consider Kolmogorov complexity, and then various resource-bounded variants of Kolmogorov complexity. Levin's version of Kolmogorov complexity K little t, which we'll define soon. KS, which is space-bound Kolmogorov complexity, polytime-bound Kolmogorov complexity, and a version of Kolmogorov complexity defined and studied by Allender, which is closely related to circuit size. Okay, so first of all, Kolmogorov complexity. I mean, yeah, you might be familiar with this material, but yeah, just want to make sure that we're all on the same page. So how do we define Kolmogorov complexity? We have some fixed universal Turing machine U, right? So U is a fixed universal Turing machine, and Kolmogorov complexity is defined with respect to that. So this is quite different from circuit complexity, which is more of an absolute measure, right? It's just the circuit size, it's very concrete. While here, everything is done with respect to this fixed universal Turing machine, which is kind of implicit. So for any string x in sigma star, let's say sigma 0, 1, k of x is just the minimum size of a program such that the universal machine generates x on an empty input, right? So the program on an empty input generates x. And similarly, there's a sort of a conditional variant where you start off with an input y, and you look at the smallest program that generates x from y. And these conditional variants have been studied quite a bit recently as well. And so I just thought I'd introduce them here in this context. You can define a conditional variant for any measure. So intuitively, k of x is the size of the smallest program that produces x when run on the empty string. And just as some simple examples, so k of 0 to the n of string of zeros is at most log n plus order 1, since we can just sort of encode n into the program and then tell it that it's the program, tell the program that it's essentially n zeros, order 1 bits to describe a program that outputs 0 to the n given n. So that's at most log n. And for certain n's, it might be much smaller. And a more kind of interesting example, if you take the first n digits of pi, then first n bits of pi, the Kolmogorov complexity of that is also at most sort of log n plus order 1, because there's efficient procedures to generate the first n bits of pi given n. So this kind of like Kolmogorov complexity gives you a sense of the complexity or the randomness of a string. So yeah, and most strings are structured. The strings produced by short programs are the ones that are structured. So just a couple of basic properties of Kolmogorov complexity. First of all, every string has Kolmogorov complexity at most its length plus a little bit, because you can describe the string just by giving a program that's the string itself together with the instruction to just copy it out, right? So the program has x in it, and then you tell the program that it just needs to copy x out into its output tape. That's the extra order 1 bits, and this is describes x precisely. So so this is the case for every x, and from now on, I'm going to be ignoring the universal machine. I mean, for the purposes of this workshop and this program, mostly the universal machine doesn't really play a big role, because if you switch to a different universal machine, that changes the chromotype complexity by at most a constant. And these constant additive terms don't seem to make a difference in practice. When there's some exotic kind of results where they do, but for the purposes of this workshop, really not. So we just assume they fixed a universal Turing machine and work with that. And so we have this sort of like upper bound for any x that chromotype complexity is at most the length of the string. And we also have this low bound that most strings are hard, require chromotype complexity at least n-1, for example. And this is by straightforward counting argument. I mean, for any I, there's going to be at most 2 to the I strings of chromotype complexity I, since there are at most 2 to the I descriptions of length I. A description is just a program of length I, and there's at most 2 to the I of those. Each one can produce at most 1 string. So there's at most 2 to the I strings of this kind. And so there's at most 2 to the n-1 strings of chromotype complexity less than n. So there's got to be some string which has chromotype complexity at least n by the pigeonhole principle. And if you look at, for example, the threshold n-1, you get that at least half of all strings of chromotype complexity at least n-1. And such counting arguments are going to apply to any sensible measure of complexity that you pick. But yeah, I'm just kind of giving you the argument for chromotype complexity. Okay, so that's chromotype complexity as a measure. And what about the metacomplexity problem? The metacomplexity problem is, again, you're given the input a string together a parameter, and the question is whether the complexity is small, right? Whether the k of x is at most s. And then we also consider these sort of like functional problems, where instead of having a yes/no answer, instead of a decision problem where you have a yes/no answer, you also actually compute the complexity. So k is just a problem given a string x, compute the k little, sorry, this should be k complexity, not k little t complexity. That's a typo. Compute the k complexity of x. And it's not too hard to see that these two problems are sort of interreducible to each other. If you want to reduce mkp to k, you can just sort of like compute k and then check whether the complexity is at most s or not, and output yes if it is. And if you want to reduce k to mkp, then you can just run kind of the algorithm for mkp with every possible s from 1 to n and pick the smallest one, and that's going to be a chromotype complexity, right? So these two problems are going to be equivalent with respect to polynomial time reductions, but yeah, sometimes it's useful to consider one and sometimes the other, which is why I'm measuring them both. And they're both uncomputable, and we're going to see the proof of that soon. As I just said, they're reduced to each other. Hence, it's sufficient to consider one of them when analyzing the complexity. Okay, so this is an argument that you might have seen before, but let me review it. So the uncomputability of chromotype complexity. Why is chromotype complexity uncomputable? Assume for the sake of contradiction, there's a Turing machine M that computes k. We will kind of like arrive at a contradiction. So we define the following Turing machine N that accepts x if and only if the chromotype complexity of x is at least n. And by the basic property of chromotype complexity we saw on the previous slide, n accepts at least one string for each input length n, right? So since we assume there's a Turing machine M that computes k, this is sort of like a valid Turing machine, and it accepts at least one string for each input length n. And now we can define a sequence of strings as follows: x sub n, where x sub n is of length n. We define x sub n to be the lexicographic first string of length n that capital N accepts. We know the capital N accepts at least one string of each input length. So there's got to be, so x sub n exists for each n. And now notice that we can compute x sub n given n by just simulating n, capital N on strings of length n, little n in lexicographical order and outputting the first such string it accepts, right? Because n is a decider. N is a Turing machine that always halts. And we can just sort of run it on the strings of length n until we find one on which n accepts. And so this gives an algorithm for computing x sub n. So this implies that k of x sub n is at most log n plus order 1, because given the description of n, which is just log n bits to describe n, and this program, we're able to output x sub n. But by the definition of x sub n, k of x sub n is at least n, right? Because n accepts only strings of high complexity. So this is a contradiction for large enough n. So this is a kind of like diagonalization argument that's quite kind of common when considering chromotype complexity and its variance. But just want to give you a taste of that, a reminder of it. And also I also want to mention something that's kind of like relevant to the question of proof complexity. So all of this is sort of like very straightforward. I mean, like pretty elementary, but these elementary considerations are kind of related to deep issues and foundations of mathematics. So to questions such as or results such as Gödel's incompleteness theorem, that no sort of consistent axiomatizable proof system can prove all truths about the arithmetic of natural numbers. We can prove like very strong incompleteness result by arguing about Kolmogorov complexity in a similar way to how we showed uncomputability. And so this is just sort of a variant of the argument we had before, but let me tell it to you. So like this sort of indicates a deep intractability of Kolmogorov complexity as a measure. And this is the theorem of Chaitin. So let X be any sort of effectively axiomatizable sound proof system. I'm not going to define that, but it's sort of just just intuitive what it is. So consider any sort of proof system like piano arithmetic, which is effectively axiomatizable and sound. Then there's only finitely many integers m for which a statement of the form that the Kolmogorov complexity of X is at least m can be proved in X. So in a sense, the truth about which strings have high Kolmogorov complexity is inaccessible to any standard proof system. There's only finitely many m for any given proof system where you can prove a statement of this form. And this proof, again, is by a similar diagonalization argument to how we saw before. I mean, suppose for the sake of contradiction that there are infinitely many m for which the statement is provable in X, we can then figure out how to find such an X given just a description of m. Because given m, which can be represented by log m bits, we can computably find an X such a k of X is at least m is provable in X just by enumerating all possible proofs of such statements in parallel until we find one, right? We know that one exists. By assumption, there are infinitely many m for which this is provable. So we know that one such statement exists, and we can just like look for proofs by a dovetailing argument in parallel until we find the first one. But this X that we find has now been described with log m bits. So it has Kolmogorov complexity at most log m plus order 1. And again, for large enough n, this contradicts k of X at least m. So if you prove the statement k of X at least m, that should be true by the soundness of the system. And this is contradiction to the upper bound of Kolmogorov complexity of X. So it's a very simple argument, but it has sort of very kind of like powerful consequences. And if you're feeling pessimistic, then you might think, well, I mean, it's a possibility that some sort of analog as a result might hold for complexity theory, that instead of Kolmogorov complexity, if you look at, say, circuit size, and you look at proof systems which you work in, that maybe proving circuit low bounds is hard for a similar reason. But yeah, let's not be that pessimistic for now. It's just kind of something useful to know about in general. Okay, so having defined Kolmogorov complexity, I mean, that's not going to be of very much interest to us because it's uncomputable, but there are all these kind of resource bounded variants which will be useful to us and interesting to us. So let's get into them and say a bit about them. So so these are variants where you look at like restricting the running time of the Turing machine or somehow charge the Turing machine for the time that it runs for, right? So if U is a fixed time efficient universal Turing machine, we can look at k little t of X, which is the minimum of the program size plus a log of the time which is required to generate X, right? So the log of the time that required to generate X from P. So earlier we were just charging the program for its size. Now we also charge it for its time, the time that it's taken to produce X. And similarly to before, we can show that for every X, k little t of X, there's no size of X plus log of size of X. This extra log term is because we can use a program that just represents X and copy it out into the output tape, but now that runs in linear time. So t is linear in size of X. So that creates this additional, because of this additional term, it creates a log size of X term here. And then, but by counting arguments, as before, there's a string of length n such that k little t of X is at least n, and at least half a string such that k little t of X at least n minus 1. So note that Kolmogorov complexity is at most k little t of X because you're charging in addition for the time here, and Kolmogorov complexity just charges for the program size. So this always holds. And why is k little t interesting? So I mean, for our purposes, it's interesting because it's we'll see the next slide because there's a problem in exponential time, which is sort of complete for that class. But it's interesting in general because of Levin's universal search algorithm, which is sort of like this cool idea where if you're looking for the optimal time required to solve a search problem. Suppose we have a polynomial time computable relation R, and we want to find a y for which R of y holds, and we know that such a y exists. What's the shortest time in which we can find such a y? We can kind of characterize that in terms of k little t complexity. So this can be done in time t of n times poly of n, if and only if there's a witness y with small k little t complexity. And this again is not too hard to show. I mean, one direction is that if you can do it in time t of n times poly of n, then you're effectively generating this witness y just from the description of n in time t of n. So essentially the cost of that will be log t of n for the running time and log n for the program size. So that's what you'll get for the KLT complexity of y. So one implication is easy to see, but for the other implication, essentially there's sort of like this optimal search idea, which is that you just look for witnesses in order of KLT complexity, of increasing KLT complexity. And if you do this carefully, you'll see that you can do it in time that's at most T of n times poly of n. So so this is kind of like cool relationship between kind of like the optimal time for a certain search task and this Kolmogorov complexity measure, which points at why it's an interesting measure. Yeah, question.
Symbol of the class and parameters.
Sorry, do you mean little t or capital T? Yes. Oh, little t. Oh, so do you mean here and here?
Yes, because if I put here,
there are two different teams. It's just part of the name.
It's just part of the name.
yes, so what is T then?
I mean, sorry, KLT is just think of it as atomic. It's just a name.
Inside the equation, T is part of the name. Right inside it's there.
But given a certain program P that outputs X, it takes it T steps to output X. So then I'll take the size of P plus the number of steps. You could call it a different letter.
Yeah, I think it's confusion because of concatenation. Yeah, I mean, this is just a name. KLT is just a name. Yeah, anyone else? Okay, so MetaComplexity question about KLT is, well, I mean, again, this input is a string to give the parameter. The question of whether the KLT complexity is of size at most s. And the search problem, or the functional problem, rather, given string x, compute the KLT complexity of x. And an observation is that these problems are in exponential time because you can just sort of like, yeah, I mean, like the exhaustive search algorithm is in exponential time because if you want to like try all strings of KLT complexity at most n, that takes exponential in n time, just by taking a brute force search for optimal program. So you can just try various programs in order and find the one for which p plus log t is smallest, and that takes exponential time. And in this great paper, which kind of has been very influential in the area, I mean, Eric Allender and others showed that MKLTP and KLT are hard for exponential time under various kinds of reductions, under non-uniform polynomial size non-adaptive reductions. So it's not very important exactly what these reductions are, but under some reasonable notional reductions and non-deterministic polytime Turing reductions. So in fact, for KLT, we know that it's actually hard for X. So it's in X, but it's hard for X. So it's complete for X under such reductions. So this is a case where the MetaComplexity problem is sort of like representative of the complexity class. And we dream that something similar might be possible for NP and for time-bounded versions that are in NP. Note though that this kind of hardness result is still insufficient to establish that this problem is not in polynomial time, because from MKTP being in polynomial time, you just get that X present poly size or X equals NP, both of which are possible. We haven't ruled them out yet. So we still don't know how to show that MKLTP is not in P, and that's sort of a major open question about KLT. Sorry? No, it doesn't. Yeah, and then there's sort of like K capital S, which is sort of like a space bounded version. So very similar to KLT, except that now you consider the minimum program plus space bounds such that you produce a string in space at most S. And we have a similar bound, upper and lower bounds for K capital S. And K of X is at most KS of X. So just as with KLT. And so yeah, sorry, this should be polynomial space here. So just as KLT, MKLTP and KLT are in exponential time, these problems are in polynomial space by doing a brute force search. And analogously to KLT, these problems are known to be hard for polynomial space under similar kinds of reductions. In fact, you can get a better hardness result with probabilistic Polytime Turing reductions here. But again, we don't know that MKSP is not in log space. So that's an open question about the space bounded version. And then this polynomial time bounded Kolmogorov complexity, where you just sort of like, so this isn't a fixed problem, but it's a family of problems. So if you fix a polynomial time bound T, and you kind of like, so there shouldn't be a log T here. Here, you're just counting the program size. So the minimum program size such that U of P, epsilon equals X, and at most T of size of X steps. there isn't this additional log t term. That's a mistake. So that's a way of kind of like restricting congruent complexity to fast programs that run in time polynomial in the size of x. And again, there's kind of some easy upper and low bounds and kind of relationship with congruent complexity. And again, we can define these sort of like meta-complexity problems. And in this case, they're in NP because we can kind of like guess a program and check in polynomial time that the program outputs the string, a program size at most s, and check that the program outputs the string we have as input. And yeah, and then you get also a way to compute the complexity exactly in Polytime with an NP oracle. And it's open whether any of these problems are NP hard. So that's a big open question. However, all of them are hard if one-way functions exist. This has been known for a long time due to the National Proofs paper and the work of Cabinets and Tsai. And statistical zero knowledge is not reduced to them all. That's work of Allender and Das. And finally, so yeah, we've already seen quite a few of these measures, but finally K capital T, which is the notion defined by Allender. So here you assume you have a Turing machine which has random access to its states, which can kind of like access any cell of its state, in kind of like logarithmic time. And we do this so that it makes sense for the machine to run in sublinear time. We want to kind of like define what it means for machines to run in sublinear time. And to do that, we have random access. And then we define this notion where we, again, kind of like cost for time, but now we cost for t rather than log of t. Except that now you're not asking the program to output x fully, you're asking it to output x implicitly. Given kind of an index in x, you wanted to output that bit of x. So given an index I in x, you wanted to output the ith bit of x in at most t steps. And if you think about it, this kind of like feels a bit similar to circuit size, where also you kind of like, you're outputting a fixed bit of the truth table in size s, right? With circuit size. And similarly, you're outputting a fixed bit in time at most t. And so again, the sort of like, yeah, easy to prove upper and low bounds. One of the reasons why Allender defined this notion was to find a version of congruent complexity that relates to circuit size. It turns out that K capital T and the circuit size are polynomially related. But K capital T has some nice features in the sense that like these counting arguments mean that the strings of kind of maximal K capital T complexity, which would be K capital T. So the strings of maximum K capital T complexity. But we don't know the same for circuit size. We don't have a very kind of precise sense of what the maximum circuit size is. So we have sort of like better sense of how K capital T complexity is distributed than of circuit size. And that's what makes this interesting to study.
I is encoded in binary here?
Yes, right. Yeah. I is encoded. Yeah, that's right. Thanks. And again, yeah, we can define the metacomplexity problem, and that's an NP. And it's open whether it's NP hard. And just as before, it's hard if one-way functions exist, and statistical zero knowledge reduces to them to these problems. Okay, so understanding the complexity of individual metacomplexity problems is challenging. Yeah, but it also seems very hard to come up with reductions between them in the worst case setting. So there are all these questions that we have about for each of these problems, what the complexity is. And it's not so easy to find relationships between these questions. For example, it's even unclear whether if with MCSP, if you have like threshold capital N to the 0.5, whether it reduces to MCSP with threshold capital N to the 0.1 or the other way around. It seems kind of quite hard to establish such reductions. And it's also hard to establish kind of reductions between these problems, between say MCSP and K poly or MCSP and K capital T, though we know the circuit size and K capital T are polynomially related. So there's some kind of things that we know, like all of the above problems, polynomial time reduced to congruent complexity, except maybe KLT, but and even that's not trivial. So there's some things that we know, but essentially no reductions are known between these resource-bounded different metacomplexity problems.
Well, I think you can reduce MSP N to the 5 to MSP N to the 1, but the other direction don't know. So you just continue to your truth table for like N to the 0.4 times. That seems like a rather good.
So it might be in one direction that it goes about, yeah. Okay. Yeah, so that might be the case. So yeah, it's not completely sure, but certainly reducing between various measures is difficult. And with the same measure, sometimes I think using like padding kinds of arguments, you could maybe reduce between them. So these are all sort of like worst case kind of like questions. And it turns out that with the average case setting, the things are somewhat cleaner and more robust. And one of the nice things about these metacomplexity problems is there's a very natural distribution, namely the uniform distribution on instances of metacomplexity problems. But in order to consider average case complexity with respect to this distribution, we need to consider zero error complexity, because metacomplexity problems typically have far more no instances than yes instances. So if you consider kind of average case complexity where you can make errors, then you can always just say no, and that would be an efficient algorithm that's correct. So it makes sense instead to consider zero error complexity. And this turns out to be closely related to the natural proofs of Ross, Brown, and Rubich. I should point out that it's also kind of interesting to consider bounded error average case complexity. You just need to use different distributions. And in fact, that's how Liu and Pass showed like this connection with one-way functions. And there's other results which use bounded error average case complexity. So both of these kind of notions of average case complexity are interesting for metacomplexity problems. I just want to point out that we only looked at worst case complexity so far, but the average case complexity setting is interesting too. And there's different sort of distributions and kind of notions of average case complexity you can use. And there's also approximation variance. So in fact, there's at least two natural notions of approximation we can consider. The first is where you approximate the complexity of a string. So you want to distinguish, say, strings with high k little t complexity from strings with low k little t complexity. And the second is where you're trying to approximate the string itself by a low complexity string. So for example, you want to distinguish between strings, say, if you look at like circuit complexity, you want to distinguish two tables of functions that have small circuit size from functions that are far from having small circuit size, meaning that they have relative Hamming distance at least, say, 0.2 from any function with circuit size, capital N to 0.1. And these are both interesting and arise in kind of natural ways. The first comes up, for example, in worst case to average case reductions for metacomplexity. We'll see that as the bootcamp goes on. And the second comes up in applications of learning theory, because in learning theory, when you're learning circuit, you're typically interested in learning like a circuit that approximates your function well. And that corresponds to the notion of approximation here. I'm just kind of like going over this a little bit more quickly because I'm kind of running out of time. But yeah, so I just want to spend a little bit of time on these last 4 slides where I think very, very briefly talk about metacomplexity as a tool. So far, I've mostly spoken about metacomplexity as a topic. What are these measures? What are the problems associated with them? What's the complexity of these problems? But I want to say a little bit about the broader kind of relevance. And that will be kind of much more the focus of my talk later, where I'll be kind of showcasing these open problems that in different areas that have sort of connections with metacomplexity. But for now, just to give you a high-level idea of why metacomplexity is useful. Well, for circuit complexity, it seems natural that metacomplexity will be useful because every no instance of MCSP corresponds to a circuit low bound. Namely, the function f doesn't have circuits of size s. Conversely, all circuit low bounds are encoded into the problem. So in a way, it's a problem that captures information about circuit low bounds. So it makes sense that to be relevant to circuit complexity. There's been like a long line of work where essentially all known circuit low bounds for explicit functions have also been shown for MCSP using connections with pseudo-randomness. So in a way, it's interesting that, yeah, I'm not sure that all such strong low bounds are known for SAT, but for MCSP using kind of like techniques from pseudo-randomness, we can capture almost all known circuit low bounds. So it's underway in MCSP is related to circuit complexity. And also there's a sort of like hardness magnification phenomenon, which is kind of interesting for MCSP and other metacomplexity problems, where for certain parameter values, if you show just like slightly non-trivial low bounds, for example, if you show that MCSP with capital N to little o1 parameter does not have circuit of size N to 1.01, then that gives you a very strong complexity implication, namely the NP doesn't equal P. So this is kind of like phenomenon, which is interesting for metacomplexity. There's so multiple reasons why metacomplexity is kind of connected to circuit complexity. And then there's kind of relevant to learning theory as well. I mean, learning is closely related to solving the search versions of MCSP and other metacomplexity problems. So here the learning model is, so the learner is given oracle access to a target function, and it outputs a good hypothesis if such a hypothesis exists. So good hypothesis may be one that approximates the target function well. And this is kind of like close to solving the search version of MCSP. Given a truth table, output a small circuit for the truth table if one exists. Right? So, so this is sort of like you have a witness, which is a small circuit, and want to output that witness. A witness that's at least a good approximation to the original truth table. And intuitively, as an efficient learner, one can solve the search version approximately just by running the learning algorithm and kind of answering all oracle queries by looking at the truth table. And then finally, you can even check that this hypothesis output by a learner is correct by just going over the truth table and seeing that it's a good hypothesis. So learning implies that you can solve the search version of MCSP approximately. And this very influential paper of Kametzino and Palgazzo, Cabinets, and Kolokolova showed that, in fact, the converse, there's a converse to this as well, that even an efficient decision procedure for MCSP, even if you have an efficient algorithm for MCSP, we're given an entire truth table that can be used to get efficient learners. So yeah, this is a paper that's had like a lot of impact in this area. And then the relevance to crypto, just kind of one reason why MetaComplexity is relevant to crypto. If you look at SURAM generators, which are essential to encryption and other cryptographic tasks, a SURAM generator, what it does is it maps short random seeds to longer pseudorandom strings, and these pseudorandom strings are indistinguishable from random strings. And just one observation is that the outputs of the PRG all have low complexity according to these various measures that we've defined, because they can be generated from a short seed efficiently. So that implies for various measures that they have low complexity. And just by counting arguments, purely random strings do not have low complexity. So the security of PRG relies on not being able to distinguish low complexity strings from high complexity ones, because purely random strings have high complexity and the outputs of the PRG have low complexity. So what this shows essentially is that pseudorandomness implies the hardness of MetaComplexity, but in fact, the converse is true as well in various settings, and this work of Leon Pass and others sort of establishes this. So this is sort of just one reason why MetaComplexity is relevant to crypto, and there are others. And finally, the relevance to proof complexity through the natural proofs barrier of Ross-Brown-Rudich. So Ross-Brown-Rudich identified this barrier to circuit low bounds against strong circuit classes by showing that known explicit low bounds against weak circuit classes satisfy this property. But under standard crypto assumptions, there are no proofs against strong circuit classes, such as the class of polynomial-sized Boolean circuits. So they sort of drew a boundary between the low bounds that are known thus far and the low bounds we want to show for circuit classes such as formulas or general Boolean circuits. And natural proofs turn out to be very closely related to MCSP. So existence of natural proofs is equivalent to efficient zero-error average case algorithms for MCSP. And thus, like the interactivity of MCSP is sort of crucial to the meta-mathematical barriers to circuit low bounds. So in a way, it's not just about MCSP, it's not just around the complexity low bounds, but also the barriers to complexity low bounds. So, I mean, yeah, this is all fairly quick. I just want to give you like a very, very kind of like rough sense of why there's connections to these different areas. And in the next talk, I'll kind of like go into several problems in more detail and kind of give you the background and the connection to MetaComplexity, just to kind of give you a sense of concretely which kinds of directions might be interesting to look at. That's all I have. Thanks.
We have time for questions.
This result? Oh, it's just an observation. It's in a paper with Shuichi and me, but it's just an observation. Yes, that's a good question. I mean, in fact, when I give my next talk, algebraic circuits will come into it. I think Ido was asking, what about other models of circuits like algebraic circuits, maybe quantum circuits as well? I don't know. But so I was just saying that in my next talk, I will say something about algebraic complexity. And yeah, and so there are directions kind of connected to quantum computation as well. Is there like a notion of metacomplexity there? Which, I mean, there's been a little bit of work on it, but I think there's still a lot of work to be done understanding that. Yeah.
There's a coffee break and we'll resume at 11.